Okay, so welcome to Math 383 Complex Analysis. So I am Professor Miller. So if I'm in my office, it is office hours. The first day or two is going to be a little bit hectic. I will be sending an email later today about when I'll be around later today and this weekend if people want to get together and just chat a little bit and find out more about the course. Okay, so I want to just start with some brief introduction to, is it showing you the slides? Does it say objectives on your slides?
No, we just see the first slide.
No, we just see the first one.
All right, let me try again. How about now?
Yep.
Okay, and now it's moved to introduction.
Yeah.
All right, this is why I have two devices. So one device is trying to just mimic what you're seeing so I can tell if things are not working. Okay, so goals for the class. Obviously, I want you to learn complex analysis. This is an absolutely beautiful subject. It's used in a variety of places, from pure mathematics to industry, finance, physics, lots of different applications. Depending on what you're interested in, I'm absolutely happy to try to adjust a little bit about what we're going to cover, what we're going to look at. I want to emphasize techniques. I want to emphasize asking the right questions. So how many of you remember looking at tables of integrals when you were in high school? And you're going to have to be, unfortunately, a little bit vocal because I can't really see everybody today.
Yes.
Yeah.
Kind of.
Okay, so people do still vaguely remember using tables of integrals.
Yeah. Yes.
So the difficulty is that your books can only have so much space, and it was a real skill to learn how do I convert what I'm doing to the form that's in the book. And when I was in high school, we spent a lot of time looking at that. Nowadays, with modern packages like Mathematica, with Wolfram Alpha, these things are done automatically. The computer just has a bunch of standard algorithms that it tries to convert. And so in terms of what I want you to get, a lot of the content is no longer as important to learn as it used to be because it's so readily available. A lot of it is learning to ask the right questions and to have the background, to have the information available so that you can attack them. I want to help prepare you for grad school. If you want to go that route, if you want to go industry, that's fine as well. This is meant to be a graduate level course. It's meant to be taught at a fast pace. I am not going to cover the proofs of every result in class. When I was a freshman, I had a very proof-intense course. And for the longest time, I thought Rita was the greatest mathematician of the 20th century because every proof seemed to be left to Rita to do. We're not going to be that bad, but a lot of it is going to be left to you to do. If you have questions, please speak up in class. Please talk to me in office hours. When I was teaching differential equations at Williams in my first year here, linear algebra is not a prerequisite. And I wanted to do some 2x2 systems of equations, and you need a little bit of matrices for that. And so I asked the class, is everybody comfortable with 2x2 matrices? Does anybody want a review? And nobody wanted a review. And I said, so everybody's fine. Okay. This was so long ago that people didn't have phones as a guarantee, but I had clickers that I could pass out. And I told people, press 1 if you want a review, press 2 if you don't. I'm not going to report the results to the class, I'm just curious. Well, I never said I wouldn't report them to other people. 43% of the class wanted a review. 0% was willing to speak up and ask for a review. So if there's something that you want me to cover, almost surely other people in the class would like to see that as well. And so I'm going to try to judge as best I can what to do in class and what to leave to you to do at home or to come and see me. There's a lot of material to cover in complex analysis. There's no way that we can cover it all in one semester. So, towards the end of the semester, I want to do a little bit of just showing you where do things go. If you were to continue, what would you see next? And just have these on your radar screen. But, again, if there are things that you want to see, let me know. Related to this, please speak up in class. And at the end of each class, shoot me a little email telling me, what did you say? Most days I'm actually going to be in the room and I will see who's saying what, but today it's going to be much harder. I have these disembodied voices in the background. I can't really see anybody. shoot me an email so I know, who you are and what you said. One of the reasons I want you to do this is I want you to get comfortable speaking. When I was an undergraduate, I was absolutely terrified to speak up. And it wasn't until graduate school when a friend had me become a social chair that I actually, overcame my shyness. You want to be comfortable speaking. You're going to be talking to potentially professors, you'll be speaking at conferences, or you'll be talking to bosses or clients, and you want to be comfortable talking about technical material. I want you to gain some expertise in writing proofs. And so this is a class where we're going to be assuming real analysis as a background. A lot of the results in real analysis we're not going to need. There will be a few of them that will occasionally become useful, and you're happy to review them as needed. It is very easy to have a proof that is mostly correct, but has one or two gaps where you just accidentally assumed something and you didn't realize you were doing it at the time. At some point in the semester, I will give you my proof of the Riemann hypothesis. If you know what that is, this is one of the biggest open problems in mathematics. You would get at least $1 million if you solve it properly. Obviously, there's a mistake in my proof. There's one small gap. And it's very easy to have small gaps. For the record, since this is being recorded, I knew as soon as I wrote it that there had to be a gap. It took me a while to find what it was, but I knew there had to be something there. The last thing, and this is a little bit related to some things I've just mentioned, is I want you to see applications of earlier courses. There's a reason why we've had you, take these classes and learn this material. Is you've spent some time learning real analysis, learning multivariable calculus. Now we can use those results and do a lot more with it. And so we're going to build on a lot of those results. Okay, so types of problems. So this is just a set of things that I'm interested in. I'm absolutely happy to add some things to the list. So I was trained as a number theorist. Interestingly, I was trained in number theory by a nuclear physicist when I was an undergraduate. So I do speak number theory with a physicist's accent at times. There's a lot of wonderful applications of complex analysis in physics, especially the Heisenberg uncertainty principle. If you know what that is, it's really a statement about a function and its Fourier transform. And we'll get into these topics later in the semester. The method of stationary phase is one of my favorite techniques in all of mathematics. It's a way to approximate extremely well a large class of integrals. So one of the things that becomes extremely important as you go further in mathematics is it gets harder and harder to have a problem where you have a nice, beautiful closed form solution. What you're really going to have typically is you're going to have a main term and a lower order term that's small. Does anybody remember how much Elon Musk paid for Twitter?
6 billion?
How much?
90 billion?
Say it as a number.
44 billion?
44 billion, yes, 44 billion. What if, when they were looking at the contract, they said, oh, wait, there were some additional conditions and whatnot. It's actually, $100,000 more. Would that make any difference to Elon Musk's purchase? No. Or if it was $1 million more, it wouldn't make a difference, relative to 44 billion. And so for a lot of things, you want to get a sense of what's the main term, what's the lower order term? How much do these smaller effects really matter? And for a lot of these problems, it's hard to get an exact answer, but many times we can actually get a main term and a much smaller lower term. If any of you have done probability or statistics, you might have seen the central limit theorem. And the central limit theorem is a terrific example where if you have nice random variables and you look at the distribution of the sample mean, that converges to being normally distributed. And if the distribution is nice, you can even quantify how quickly it's converging to being normally distributed. And this is definitely one of the topics we can discuss in the semester. And it's just a wonderful application of, for many things, it's enough to just know what the main term is going to be. So most of my experiences professionally using complex analysis is looking at zeros of L functions. So if you've seen the Riemann zeta function, looking at something like that, or if you've seen matrices, it turns out a lot of physical problems can be modeled by matrices. And what we can do is we can write down a matrix which describes the system and try to understand the eigenvalues of that. And those eigenvalues correspond to energy levels. And so complex analysis occurs a lot in problems like this in terms of trying to understand what's going on. All right, so course mechanics. So we are going to be moving at a fast pace. So for those of you who are applying to graduate school, if you want a letter of recommendation from me, I will be writing that this class is taught at a graduate level. I actually check with colleagues of mine who teach this at graduate schools with graduate students so that I can make this statement. You should be reading the book before class. This does not mean that if we were unable to solve the technical glitch today, you would be able to give the lecture, but you should have some rough idea of what are we going to be talking about. What do the symbols mean? What are the things in play? So homework, 15% midterm, 40% final, 40%. If you want, you can do a significant project involving complex analysis, and I'm happy to then adjust how much everything else is worth. So if that's something that you're interested in, let me know. It's hard here because I can't see everybody's faces. How about everybody yell out if you've seen Green's theorem?
Yeah.
All right, and yell out if you haven't seen Green's theorem.
No.
So I was not able to hear too many voices one way or the other. So if you've seen Green's theorem in multivariable calculus, that's a huge plus right now, because it turns out that one of the main results in complex analysis is essentially Green's theorem. So if you haven't seen Green's theorem and you want to get a quick sense of what that is, here is a link to Green's theorem in a day. And so this is a lecture I gave in math. It might have been so long ago that Math 150 might have been Math 105 when I gave the lecture. And a lot of the ideas there apply in complex analysis as well. So for office hours, eventually I will set fixed office hour times. If I'm in my office, it's always office hours. And I'll try to keep my schedule posted online. Unlike most professors, I don't try to get to know you before the semester starts. I want you to force me to get to know you, because that's what's going to happen when you leave Williams. When you go off to graduate school, when you go off to industry, I am always up for meeting people either individually or in small groups. Happy to go for a coffee or an ice cream or a walk. Just shoot me an email or give me a phone call, and happy to try to find a time that works for everybody. Okay, so there'll be a lot of material on the webpage. I am using state-of-the-art 1990s technology. The reason is this way it is not through the GLOW system at Williams, so you can still access everything once you graduate. Seems to say prepare for class again. That must be important since it's on so many different pages. So the class is going to be fast-paced. It's going to make a tremendous difference if you can prepare for class beforehand. And again, as I've said, if there are topics that you would like to see, let me know, and happy to try to work them in. All right, so 3 pieces of advice from my brother. The first is party less than the person next to you. Next, very important, take advantage of office hours and mentoring. So when you leave Williams, you learn just how special of a place this is. People are here because they love teaching. They love being with students and colleagues. That's not always going to be true wherever you go. So, take advantage of getting to know who's in the class. This is why I send emails in the CC, not the BCC field. And then the last is, learn how to manage your time. I've known a lot of very smart people over the years who do not do a good job with time management. What this means is, if you're going to have a big complex analysis homework assignment due, make sure you leave enough time to do it. Don't plan on finishing the problems just before everything is due. Life happens, things can happen unexpectedly. And you don't want to be pushing things off to the last minute. If there is a true disaster, family member dies, you have all of a sudden a job opportunity and you have to leave for an interview you weren't expecting to do, I'm happy to adjust deadlines. But for the most part, you should be able to prepare your schedule and get things done in plenty of time. I often try to have the due dates of the homework a couple of days after we've covered all the material, just so that it's not pressed up and too tight. I can't see right now how many people are seniors who are considering a career in industry. It's almost a fifth class to be applying for jobs or looking at graduate schools and fellowships. And so again, if you have things that you know about, I'm happy to work with you to adjust deadlines. I'm also happy if you want to do practice interviews and go over some pointers on what should you do at an interview, what should you do after an interview. All right, so this is the class mechanics. Any questions on any of this? Okay. So what I'm going to do now is, since unfortunately my pen is there and not here, that's going to make things a little bit more interesting. So let's see how well I can do this. Give me just 1 second. Okay. Okay, so let me try doing it this way. Okay, so normally I'm going to have things a little bit more participatory than this, but just with how things are, I'm going to just write things a little bit more myself. So hopefully everybody remembers the definition of the derivative. And we seem to be somehow in a fancy text mode. People, okay, is this a good font size?
Yeah.
Okay, so f of x, I'm sorry, f prime of x, or df dx is the limit as h goes to 0. And then the numerator is going to be f of x plus h minus f of x somehow divided by h. All right. So is everybody comfortable with this as the definition of the derivative? This is not the definition that extends well in multivariable calculus. So as a nice exercise, what is the definition that works well for multivariable calculus? It's not this. All right, so if anybody has any thoughts, by all means, feel free to shoot me an email. It's actually a great example of how frequently we believe we know something, but we actually haven't really looked at it the proper way. And so I'll let you try to think of what's the right definition. Now for us, for complex functions, we use f prime of z equals, and now this is the nice thing about doing it like this rather than the blackboard. I highlighted this part. I should be able to just cut and paste. And what am I just doing? I'm just changing all the x's to z's. And there's my definition of the derivative. Okay. So the question is, when does this limit exist? For what functions f of z will f prime of z exist? Does anybody have any thoughts about some good choices?
Like complex polynomials.
Great. So if we have a complex polynomial, an z to the n plus dot 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 plus a1, I don't know why it keeps plus a1z plus a0, then the same proof from calculus should work as before. And it's probably worth remarking, I'm assuming everybody's seen this, we are using z equals x plus iy. Where x and y are real numbers. And I is the square root of -1. So if you go back to the proof of the derivative of a polynomial, of a real valued polynomial, the proof will go through exactly as before. So what I'm going to do is I'm going to just take a screenshot of this and just save all of this so that you will have these for the notes. Are you able to see me in the PowerPoint right now or no? You should still be seeing this box, okay. So let's consider f of z equals the complex conjugate of z. And so if z is x plus iy, can somebody tell me what the complex conjugate would be? Good. The complex conjugate is x minus iy. So f prime of z would equal the limit as h goes to 0 of f of z plus h minus f of z divided by h. And we want the same limit no matter how h goes to 0. Okay? And so the complex conjugate of z plus h is the complex conjugate of z plus the complex conjugate of h. So this is just a good exercise to show if I add two numbers and I take the complex conjugate, which is just changing the sign in front of I, that's the same as taking the complex conjugates and then adding them. So f prime of z would equal the limit as h goes to 0 of complex conjugate of h divided by h. Now, if the limit is to exist, it has to exist no matter what path we take. So can somebody give me a good path to take?
Approaching 0 along the real axis.
Good. So approach along the real axis. So h is going to be h sub x plus 0. Well, I'll say I times 0. So approaching along the real axis. So the complex conjugate of h equals h. What does the limit equal? Limit equals 1. Can somebody give me another path?
From the imaginary line?
Yeah, imaginary. So now h is going to be 0 plus I times hy. Complex conjugate of h is going to be negative h. Or we'll do this with negative h, negative I hy. Right? So the limit is, what is the limit going to be now? What was that? So what would the limit be in this case? So it's the limit. We can write it as hy goes to 0, and we'll have negative I hy divided by ihy. So that's going to be the limit as hy goes to 0 of just -1. -1. So the limits differ. So the complex conjugation function is not complex differentiable. So not every complex valued function, even every nice simple complex valued function, is differentiable. And here is a very simple example of a function that does not work. Okay. Any questions on this example? So what I want to do for the last few minutes is talk about, we now change things, right? I'll just put that there, right? So real analysis versus complex analysis. So what I want to do is I want to just state a couple of facts. Assume, let me just do one here. Assume f is complex, is differentiable. Must f prime be differentiable? What are your thoughts? If you're differentiable once, must you be differentiable twice?
It's not true for real numbers.
Okay, so false for reals, true for complex. Does anybody know an example of a function that is differentiable once but not twice as a function of a real variable? So if I give you x squared sine of 1 over x, well, let's see. Wow. So this will work. So I think this should work. X cubed sine of 1 over x if x is not 0, and 0 if x is 0. This function is clearly continuous. It's clearly differentiable everywhere except x equals 0. How do we determine if it's differentiable at x equals 0? I couldn't hear you. Could you say that again?
Take the derivative of x cubed sine of over x with like normal rules and see it as not developed.
So that could be determining whether or not the different derivative is continuous. I just want to know if it's differentiable at 0. And so to see if it's differentiable at 0, and I apologize, you might have said the right answer, I might have just misheard you, is we have to go back to the definition. Go back to the definition. And then look at f of h minus f of 0. Well, what's f of 0 going to be? That's just 0. So we look at f of h minus h over h. And that's going to be well defined. And the reason is the sign of 1 over x is always going to be between -1 and 1. Now, if we try to differentiate this twice, the sign of 1 over x, every time we pull that out, it's going to give you like a -1 over x squared. And so, nice exercise. Show f prime or f double prime does not exist. Sorry, it would be f. So I'm sorry. So this function is differential. So show f double prime or f triple prime does not exist. And the problem is when we differentiate the sign of 1 over x, it's giving us an extra 1 over x squared each time. So it turns out this is very different in complex analysis. In complex analysis, if you're differentiable once, you're differentiable twice. What can you immediately deduce from that? That you're infinitely differentiable. So if complex differentiable once, lather, rinse, repeat, infinitely differentiable. That's extremely different than real analysis, completely different. So here's another one. Assume f has a Taylor series that converges for all x. Must f equal its Taylor series in a neighborhood of 0. And just like before, it's false for reals, true for complex. So does anybody know an example of a function that does not equal its Taylor series in a neighborhood of the origin? So this is one of my favorite functions, if x is not 0, and 0 if x is 0. So this function is incredibly rapidly decaying. So if you take x to be 1 over 100, you've got e to the negative 10,000. I'm going to just quickly go to Mathematica for a second. So Mathematica is a beautiful command called manipulate. And so I'm going to do two things. First, I'm going to define f of x to be if x equals 0, it'll be 0. Otherwise, it'll be exponential negative 1 over x squared. And I'm going to manipulate, I'm going to plot f of x. X goes from minus c to c. And then c is going to go from 1 to 0.001. So that's going to allow me to zoom in. All right. And so now, if you look, I can start to zoom in, and that's the advantage of something like this. And you can just see how small this function gets. It's indistinguishable essentially from 0. It's not 0 though. And so, when I zoom out, it looks very nice. And so if you haven't used, things like Mathematica before, I will definitely happily have some classes on stuff like that. It's worth learning how to do. And so going back to text, this is a function. So nice exercise. Show the nth derivative of this function at 0 is always equal to 0. So Taylor series is identically 0, but f is not the 0 function. It turns out this function isn't even complex continuous. take z equals 1 over iy with y going to 0. And you'll see function explodes. So this is just your two nice examples of how different real analysis is from complex analysis. So let me just save that for later. Any questions on the first two examples? All right, for the third, assume f is differentiable and let's say f is bounded. Is f constant? And so can somebody give me thoughts about a function of a real variable? If I give you a real variable that's differentiable and bounded, must it be constant? Good. So for real, the answer is no. Complex, yes. So for real, oops, shoot. All right, so we've lost all the text. Oh well. So real versus complex. So 3. Consider f bounded and differentiable. Is it constant? Real, no. Complex, yes. For real, consider sine of x, cosine of x. Can anybody give me something not involving trig functions? Anybody remember the derivative of arctangent?
That's well. 1 over 1.
1 over 1 plus x squared. So that's a great example of a function that is differentiable. It's bounded, but it's not constant. So complex analysis is very different here. And here's the last one I wanted to just mention, and we will prove all these results. Consider differentiable f and a sequence of points xn such that f of xn equals 0 and the limit of the sequence of points, so as n goes to infinity of xn equals, let's call it x star, and f of x star equals 0. Must f be identically 0? So I have a sequence of points where for each of these points, my function has a 0. The limit of these points exists and my function is 0 at these points. Must the function be identically 0? Or can you give me a function that has infinitely many zeros getting closer and closer and closer to each other, and the function is not 0 everywhere? Any thoughts?
Can we use like a floor function?
I'm sorry?
Can we use a floor function?
Which function?
Like a floor function. Let's say the floor of one of the.
Okay, but is that going to be differentiable?
Oh,
They do like 1 over x, sine 1 over x, and then fill in.
Good. Always go back to what have we seen? So consider your f of x. Doesn't want to let me write. Equals, say, x cubed sine of 1 over x. this is differentiable, has infinitely many zeros that get closer and closer to 0. F of 0 equals 0, but f is not identically 0. So what I hope this does is I hope this gives you a sense of the difference between real analysis and complex analysis. In real analysis, it's very expansive. And so I'll end with the following. Okay, so let's consider, real analysis. And I have my line and I have my point 0. How many ways can I approach the point 0 if I want to take the limit as h goes to 0? How many ways are there essentially to approach? I'm sorry? 2. I basically can come in from the left, or I can come in from the right. It's extremely boring. If I now consider complex analysis, and now I have, again, I have my point 0. I can come in from the left and the right as before. How else could I come in?
The top and the bottom.
I could come in from the top to the bottom. So I could add 2 new ways. Are there other ways I could come in?
Yeah. Along any polynomial?
I could come in along polynomials. So I could come in, for instance, along a quadratic. How else could I come in?
Some like differentiable spiral.
Did you say spiral?
Yeah.
I could come in like this. Right? And then for the last way, I'll just draw it below. I could come in the preschool way. Something completely strange and absurd like this. So if the limit exists in complex analysis, that's an extremely strong condition, much stronger than real analysis. All right, I will send more details about everything. Apologies for having to do this by remote. Let me just stop the recording. All right, and then if people have any questions, just let me know.